this lecture will be focused on compressive strength calculation of strut angles. We know struts are called when a member is subjected to compressive force and used in a bracing system or in a roof truss. Then such type of compressive member is called strut, and this strut basically takes light load, means the load magnitude is not heavy, and so for lighter load and the length, effective length will be comparatively less. So, for such cases we generally use angle section to take care the compressive load. Now, this compressive load may act concentrically on the angle section or may act through its one leg, which will be eccentric, and this angle section calculation, means the strength calculation of such type of angle sections are given in code in clause 7.5 of IS 800/2007. Now, in clause 7.5.1 of IS 2007, it is told that the compression in single angles may be transferred either concentrically to its centroid through end gusset or eccentrically by one of its leg to a gusset or adjacent member. That means, when a angle section is loaded with the axial compression member, either the equivalent load, the compressive load will be transferred through the CG of this angle section by the use of gusset plate, by end gusset the load will be transferred, or it may be transferred through one of its leg, maybe in this through this leg or through this leg, it may transfer the things through this leg. So, when the angle section is transferring the load through its one leg, then the eccentricity will come into picture, and because of this eccentricity three types of things will happen. One is torsional buckling will come into picture. Torsional buckling means basically flexural torsional buckling. Flexural torsional buckling will come into picture. Another is flexural buckling, which comes for all the members, which is common, right, and another is torsional buckling. So, three type of buckling will come into picture. One is flexural buckling, another is torsional buckling, another is flexural torsional buckling. And so, the combination of flexural torsional buckling can be calculated, means from some formula which is given in the clause 7.5. Now, for concentric loading, when the angle is concentric loaded, this can be calculated through the clause 7.1.2. mean, in case of concentrically loaded in compression, the design strength may be evaluated as per clause 7.1.2 of IS 800/2007. This clause 7.1.2 we have discussed already. That means, it is a concentric loading what we have designed earlier in case of compression member, maybe that member may be channel section, maybe I section, maybe other type of section. When it is concentrically loaded, then the design formula which have already discussed, that formula will be used, which is given in clause 7.1.2. However, if this is not concentric, then we have to go for another clause, which is given as a clause 7.5.1.2. When loaded through one leg, if the angle section is loaded by the axial compressive load through its one leg. So, in clause 7.5.1.2 it is told that when the single angle is loaded concentrically through one of its leg, the flexural torsional buckling strength may be evaluated using an equivalent slenderness ratio lambda e. where lambda e is expressed by this expression, which is lambda e is equal to square root of k 1 plus k 2 lambda v b square plus k 3 lambda phi square. So, this expression you can find out in IS 800 2007 clause 7.5.1.2. Now, here constants k 1, k 2, k 3 are given in table 12. These are the constants depending upon the n condition, these constants are defined. Depending upon n condition means whether it is fixed or it is hinged, whether it is 1 bolt, 2 bolt, welded, depending on the n condition, n fixity condition, the value of k 1, k 2, k 3 is defined in table 12, which I will come in next slide. And lambda v b and lambda phi are also given in the code, which are expressed by this, where lambda v b is equal to L by R v b by epsilon into square root of pi square E by 250. So, lambda v b, the non-dimensional slenderness ratio lambda v b can be calculated from this. Another lambda phi, another term can be calculated as b 1 plus b 2 by 2 t by epsilon into square root of pi square E by 250. Now, for a particular grade of steel, this pi square E by 250 is constant. So, that can be calculated because E is constant for a particular grade of steel. So, we can find out pi square E by 250. Epsilon is also constant, I will come. Now, L is the center to center length of the supporting member. L is the center to center length of the supporting member. So, if we can calculate lambda v b and lambda phi, and if we find out the value of k 1, k 2, k 3 from table 12, then I can find out the equivalent slenderness ratio lambda e, and which is given as lambda e is equal to square root of k 1 plus k 2 into lambda v b square plus k 3 into lambda phi square. Now, here R v b, in the previous expression one term we have used, that is R v b. R v b is the radius of gyration above minor axis. That means, we have a angle section. So, when we are going to find out R x x, R y y, R u u, R v b, so this will the minimum radius of gyration will be about the minor axis, that is R v b. This is v v axis, and b 1 b 2 is the width of two legs of the angle, means b 1, if this is b 1, then b 2 will be this one. So, if one leg length is b 1, then length of other leg will be b 2, and t is the thickness of the leg, of the angle, and epsilon is the yield stress ratio, which is square root of 250 by f y. So, for a particular angle section, we can find out the properties of this, means from the geometry. From SP 6, we can find out the value of R v b for a particular angle section. Then we know what is the width of the legs of the angle b 1, b 2 and thickness of the leg. And also, if we know the grade of steel, then we can find out the yield stress ratio epsilon, that also we can find out. And this constant k 1, k 2, k 3, that can be found in table 12 of IS 800 2007. In table 12 of IS 800 2007, the value of k 1, k 2, k 3 is defined, k 1, k 2 and k 3. Now, this value of k 1, k 2, k 3 depends on number of bolts at the end of the member as well as the connecting member fixity, that means gusset or connecting member fixity, means what type of fixity is there, whether it is fixed or hinged, depending on that, and whether number of bolts are more than 2 more than or equal to 2 or 1. So, depending on that I can find out K 1, K 2, K 3. Say for example, if I have a fixed connection, if fixity is there and if the number of bolts are 2 or more than 2, then I can take the value of K 1 as 0.2, value of K 2 as 0.35 and value of K 3 as 20. So, similarly, I can consider different type of member fixity. If it is hinged, then K 1, K 2, K 3 value can be found. Similarly, if number of bolts are 1 at the end, then depending upon the fixity I can find out the value of K 1, K 2, K 3. Now, the theory, whatever we have discussed, theory means the expression for finding out lambda e value has been discussed. So, for such type of members, how to find out the design strength, that can be understood if I go through this example. So, let us take an example where an ISA 150 by 150 by 12 angle is used as a strut and has the effective length as 3 meter. Calculate the strength when it is connected by 1 bolt at each end, 2 bolts at each end and welded at each end. So, for these 3 cases we would like to find out the strength of the member, right. So, for 3 cases the 3 type of fixity will come and number of bolts, if it is 1 bolt then its condition will be different, if it is 2 bolt its condition will be different. So, through this example we will try to understand how to calculate the design strength of the compressive member of an angle section when it is eccentrically loaded through its one leg. Basically, what changes we will find out for different cases, that is the equivalent lambda, which is lambda e. So, lambda e depend on K 1, K 2, K 3. So, that K 1, K 2, K 3 can be found from table 12 and depending on the type of fixity and number of bolts, the K 1, K 2, K 3 value will change and accordingly the strength will be going to change. So, through this example we will try to understand. Now, say for example, that for ISA 150 by 150 by 12 from SP 6 I can find out the cross sectional area of the member, which I can find as 3459 millimeter square. Similarly, I need the radius of gyration about minor axis, that is given as 29.3 millimeter. This is available in table 3 of SP 6 by 1 in 1964. And for angle sections we know that buckling curve will be C. For angle section buckling curve will be considered as C, which is given in table 10. And for buckling class C, alpha value will be 0.549, which can be found from table 7 of IS 800 2007. So, these are the few things which we can find from the table 10 and table 7, that is the buckling curve is C and with respect to buckling curve the imperfection factor alpha is 0.49 and also the cross sectional area and radius of gyration about minor axis are also can be found from table 3 of SP 6 1 1964, right. So, from this data I can now find out the design strength of the compressive member as defined here. Now, for first case, if I consider the first case, that is connected by 1 bolt at each end. So, first case if I see, then I can I can see that from table 12 I can find out the value of K1 at 0.75, K2 as 0.35 and K3 as 20. So, this I can find from table 12. Now, here length L is the center to center distance length, that is 3 meter, that means 3000 millimeter. Now, yield stress ratio in this case will be, we know 250 by Fy, square root of that. Now, in this case we are using steel grade where yield stress will be 250. So, 250 by 250 is equal to 1, right. Now, I can find out the value of lambda Vv, which is expressed as L by R Vv by epsilon into square root of pi square E by 250. This I can find from clause 7.5.1.2 of IS 800 2007, IS 800 2007, right. So, from IS 800 2007, the expression given in clause 7.5.1.2, I can find out the value of lambda Vv. So, if I put the value, I can find lambda Vv as 3000, because L is 3000, R Vv we found 29.3, epsilon is 1 and pi square into E is 2 into 10 to the 5 by 250. So, after calculation we can find lambda Vv value as 1.1523, right. So, we can find out the value as 1.1523. Next, I will find out the value of lambda phi. So, lambda phi we know this is given as B1 plus B2 by 2t by epsilon into pi square E by 250. So, here B1 is equal to B2 is equal to 150, because ISA we have used ISA 150 by 150 by 12, right. So, I can put this value B1 plus B2, that means 150 plus 150 by 2t by 2t means 2 into t is 12, right. Then epsilon is 1 and pi square E by 250 is same, that will be pi square E will be 2 into 10 to the 5 and by 250. So, after calculation of this expression I can find out lambda phi as 0.1407. Now, the equivalent lambda can be found, that will be calculated from this expression, that is K1 plus K2 into lambda Vv square plus K3 into lambda phi square. So, if we put the value K1, K2, K3, that is K1 was 0.75, K2 was 0.35 and lambda V we have calculated as 1.1523 square plus lambda 3 was 20 into lambda phi is 0.1407 square. So, finally, I can find lambda E as 1.5674, right. So, lambda E, the equivalent slenderness ratio lambda E can be found as 1.5674. Now, from this I can find out the value of FCD, design compressive stress. Design compressive stress, we know the formula is Fy by gamma m0 by phi plus phi square minus lambda square to the power 0.5. So, if I put those value, I will get 250 by 1.1 by phi value we got as phi value we have not calculated. We have calculated this lambda e value. This lambda e value will be basically I did a mistake, 1.2692, right. Lambda e value is 1.2692. Now, I have to find out phi value. So, phi value, before that I have to calculate the phi value. So, phi value will be, we know, 0.5 into 1 plus alpha lambda minus 0.2 plus lambda square. So, this value if I put, I can find out the value of phi as like this. This alpha value is the imperfection factor, that is 0.49, and lambda we got 1.2692 minus 0.2 plus 1.2692 square. So, this will be 1.5674. Now, this value will be used, this phi value will be used here, phi, right. So, phi can be written as 1.5674 plus phi square, that means 1.5674 square minus lambda square. Lambda value we got 1.2692 square whole to the power 0.5. So, after calculation we can find out FCD value as 91.38 Newton per millimeter square, right. So, design compressive stress of such type of angle can be calculated as we have shown, and for this particular case we are getting 91.38 Newton per millimeter square. Now, from this I can find out the design compressive strength P d as A e into FCD, right. So, A e, the effective area, is the gross area for this case. So, this will be 3459 which we have found earlier, and FCD have been calculated as 91.38 Newton per millimeter square. So, this will be in Newton. So, this will be 316.1 into 10 cube Newton, or I can say 316.1 kilonewton. So, P d, the design compressive strength of the angle strut when it is eccentrically loaded, can be found as 316.1 kilonewton. This is the first case when two sides are connected by 1 volt. Now, the same calculations will be done when the two sides are calculated by 2 volt for the same case, and let us see how the strength is going to vary from earlier case. So, 2 volts means if I see this member, if two members are connected, if these members are connected with a gusset plate, say for example like this, then 2 volts are connected. So, similarly in this end also we can find that the member is connected to its gusset plate by 2 volt. So, for this case how we can find out the design strength of the member. So, this is case B, which is connected by 2 bolts at each end. So, for this case I can find out the value of K 1, because here K 1, K 2, K 3 will be different. K 1 will be 0.2, K 2 will be 0.35 and K 3 will be 20 from table 12. From table 12 I can find out the value of K 1, K 2, K 3, right. Now, other things will be same, because L is considered as 3000 millimeter and we are considering that both ends are fixed like earlier case. So, lambda V V will be same like previous case what we have calculated, because here nothing is going to be changed. Lambda phi also will be same as calculated earlier. Now, lambda E will be different, because it depends on the value of K 1, K 2, K 3. Okay. So, if I put the value of K 1, K 2, K 3 in the expression of lambda E, then I can find out the value of lambda E is as like this: 0.2 plus 0.35 into lambda V V square, that is 1.1523 square, plus K 3 is 20 into lambda phi square 0.1407 square. So, after calculation we can find out as this. So, if you remember that lambda E value was different for earlier case as compared to the present case. So, as lambda E value has been changed, the phi value will be changed, because phi value depends on the lambda E. So, phi value I can find out, that is we know 0.5 1 plus alpha into lambda minus 0.2 plus lambda square. So, putting the value of alpha and lambda in this equation, alpha is 0.49 and lambda is 1.03. If I put this value, then the value of phi I can find as 1.2338. So, FCD value can be found from this formula, Fy by gamma m0 by phi plus phi square minus lambda square whole to the power 0.5, right. So, if I put the value of different parameters as Fy as 250, gamma m0 as 1.1, phi as 1.2338 which has been calculated in the earlier step, then 1.2338 square minus lambda has been calculated as 1.03 whole to the power 0.5. So, from this I can find the value of FCD as 118.8, right, Newton per millimeter square. So, the PD value I can find as PD is equal to AE FCD, that will be 3459 into 118.8 into 10 to the minus 3 to make it kilonewton. So, this will become 410.9 kilonewton. So, for second case the design strength of the compressive member will become 410.9 kilonewton. Now, coming to third case, when it is connected by weld at each end. So, for this case what we can consider, that this will be similar to the earlier case. Earlier case means when the angle is connected by two bolts in both the end. So, in case of weld connection we can assume means it will be also similar, that it will be fixed at both the end, and as we have calculated the K1, K2, K3 value considering 2 bolts, for this case also will become same. So, the PD value will become simply same as we have considered earlier. That means, the weld connection and connections made by 2 bolt or more is same, right. Similar behavior we will get when it is in fixity condition, right. So, what we have seen here, that PD value for first case we got 316.1 kilonewton, and for second case we got PD is equal to 410.9 kilonewton, and in third case PD value we got 410.9 kilonewton. That means, when 2 bolts or weld connections are used, the design strength is becoming higher compared to the 1 bolt connections, right. So, if we want to increase the strength of the member, we should choose for higher number of bolts, means where 1 bolt is sufficient, we will choose 2 bolt with smaller diameter. So, that we can use 2 bolt as well as we can increase the strength of the member. This is how we can by the means we can utilize the this advantageous things, and we can make more load, means we can allow more load for such type of connections. Again, in summary, what I wanted to tell is that if member has to take more strength, then always we should go for 2 bolt at the end, means connection should be 2 or more bolt. If 1 bolt is there, means is required, then also we should try to make 2 bolt with lower diameter, so that we can accommodate more strength on the member with same member size. Member size will be same, but strength will be more, because lambda e is going to change, right. So, this is what we wanted to discuss about today's lecture regarding the design strength calculation of angle strut when it is eccentrically loaded through its one leg. Thank you.